Rockets, incredibly powerful clocks, soon lasers, what hasn't been impacted by these things?
Today on Chalk Radio, my guest is David Kaiser, a professor in the physics department at MIT, who also teaches the history of science. His course, Einstein, Oppenheimer, Feynman, Physics in the 20th Century, was recently shared on MIT OpenCourseWare. Professor Kaiser is such an interesting person to get to interview. Simply thinking about how to interview someone responsible for teaching the history of, well, everything from the Big Bang to how hippies saved physics, and yep, that is the title of one of his books, was humbling. There was so much here that we wanted to share with you, so we decided to air this interview in its near entirety. Professor Kaiser explains the earliest moments of the universe and how those moments help us understand our current night sky. We talk about how culture, politics, and even physical spaces shape how science gets done and what we might be getting wrong about Einstein. We'll also get his take on Oppenheimer, both the man and the motion picture, and how film plays a role in his course at MIT. I think you're really going to enjoy this. Thank you for being here today.
Thank you.
Let's talk physics first. Inflationary cosmology.
Yeah.
What is that, and how does it help us understand our world?
It's really our leading explanation for some of the earliest moments in cosmic history. It unfolds on what to on ordinary human scales seems like an impossibly short span of time. Most models of inflation we think about happening over a tiny fraction of 1 second when the universe was impossibly smaller than what we see around us today. And when I say a tiny fraction, I mean something like a billionth, around 10 to the minus 36th of a second or thereabouts, right? Give or take. Tiny.
Wow.
A human blink is something like, 1,000th of a second. This is just exponentially shorter literally than the blink of an eye. And yet, again, according to our best understanding, so much happened in that tiny cosmic blink that set the universe on the path that we actually now see and measure and can kind of think more about to the present day. So it was a period of very rapid, in fact, basically exponentially fast stretching of space. That's the inflation part, like an inflating balloon. Doesn't go like that for very long, but long enough to increase the size of the universe exponentially larger than anything would have been prior to that. And that really sets the conditions for our otherwise sort of more familiar and very well-tested model of the Big Bang. My very dear friend, my mentor, and now my colleague, Alan Guth, also here at MIT, Alan likes to say that inflation, which he helped to invent, it puts the bang in the Big Bang. This is what really sets the conditions for what otherwise has to unfold for our very now decades older and very well-tested model of the Big Bang. The Big Bang itself didn't explain what set the universe sort of stretching at a certain rate. It didn't explain why it would have passed through certain phases, been hot now and cold later. And those are things that inflation begins to plausibly kind of fill in and explain. And one last thing I'll mention is an unexpected sort of byproduct of that is that it gives really a first principles explanation for why there's anything in our universe at all. Why universe is not a kind of uniform smudge of just average vanilla everywhere.
Yeah.
And in fact, when we look around, when the astronomers use fancy telescopes, if anyone walking around just casually looking at the sky at night, we see one of the most stark features of our observable universe is it's very lumpy. There are regions where there's very dense concentrations of matter and then enormous voids where nothing much happens at all. I usually say it's like some parts are right by the data center and otherwise are really quiet and boring like over at Harvard. I'm kidding.
Oh.
The point is, I'm teasing. But there's a kind of distribution to the matter, to where the stuff is, to the matter and energy and activity in our universe. And how did that ever take that form? And inflation gives us a really incredible framework to really calculate quantitatively, not just to kind of wonder about it in a cartoon level, to calculate in very fine-grained detail the initial unavoidable quantum jitters, going all the way back to Heisenberg's uncertainty principle, that matter must have been subject to even during inflation. And those originally very short, small-scale quantum fluctuations on this model get stretched unbelievably fast to be the size of galaxies or even beyond galaxies, having started much smaller than the size of an atom. And it sets in motion the initial very minor lumpiness. And then over time, the areas that happen to be slightly more lumpy, slightly more mass than average, those attract more mass or matter to them through ordinary gravitational attraction. Regions that happen to be just ever so slightly underdense, a little less dense than average, those get basically further and further evacuated by the neighboring lumpy or more massive parts. And we can fill in that simple sounding story, a lot of hand waving story, now with some very sophisticated calculations and simulations, compare with really fine-grained measurements on the sky, and the match is sort of breathtaking. That was a long answer, but I think inflation is best understood as a framework for trying to understand some of the earliest moments in cosmic history and how it set our universe onto a path that we can now try to make sense of in more recent times.
Wow, it's just fascinating. It's so interesting. And like that in and of itself might be enough to fill an entire career, right?
Yes.
But yet you have this intense interest in the history of science and physics. And I'm so curious how that started for you.
It goes back a ways, not quite to the time of the Big Bang. It feels like that as I get older. It's been that long, not quite that long. But it does go back to my teenage years, high school student. In hindsight, other historians have filled in, that really turned out to have been a kind of golden age for popular science publishing. I was a lucky beneficiary, as many of my kind of peers or cohorts were, reading books in, say, the early, mid-1980s. That's the period I have in mind when I was basically a younger high school student. And so there were lots of really high-quality books, some written by practicing scientists, some written by very careful and excellent writers who were kind of science journalists or science writers who had a strong background in the science as well. So I was just gobbling these up as a kid. And some of those books from that time period used kind of history, or maybe I'd say chronology, to motivate, to kind of tell a story, to put something like a human face on what can otherwise sound like abstract ideas, whether it's about quantum theory or the Big Bang or relativity and gravitation and black holes, whatever. And so by the time I entered my undergraduate studies, I was hooked. And I remember very clearly, it was before even classes had begun, my very first few days on campus as an undergraduate, I was talking with someone who would become a very important physics mentor to me, and I shared all these kind of youthful enthusiasms about these sort of amazing stories about Albert Einstein and Niels Bohr and all these they felt to me like giants on a mountaintop.
Yeah.
And it was Joe Harris, who was an expert in relativity, longtime physics professor. By the time I got to know him, he said, there's a whole field of study called the history of science. He left out the dummy. Like, how did you not know that? I didn't know. I had never heard of it. But Joe very sweetly said, there's actually more to that than just kind of heroic tales of lonesome geniuses, which are the kind of books that I've been absorbing. They were kind of, frankly, very, very hero worshipy with hindsight. And it was Joe Harris who said, there's so much more interesting, human stories to be told. And it's not only individuals, it's institutions, it's broader cultures, it's politics, it's geopolitics, it's the stuff of World War and everything in between. And so Joe gently encouraged / nudged me to go meet with actual card-carrying historians of science. And I was very lucky to fall in with two of them. So I met very early, Richard Kremer and Naomi Oreskes, and I sort of never looked back. So they took me under their wings, and I began doing sort of essentially a double major as an undergraduate, because they showed me there's a disciplined study of history, including the history of science, that really can go beyond these kind of fairly one-dimensional stories, as I say, that I kind of loved, but really maybe ultimately were a bit limiting that I read in those earlier books.
There's something so interesting about putting a face to science, a story that makes it so much more accessible to everybody. Tell me a little bit more about something I've heard you say, that science doesn't exist on its own, that it's always happening in a context, shaped by an institution, shaped by the people around the scientists. Like, tell me a little bit more about those ideas.
Yeah, on the one hand, it's sort of a straightforward observation, right? Scientific research is now and has always been done by people, by humans, right? Not always by sometimes a very select or even elite group of people, but by people, by humans. And so it has always, by definition, been a human activity. How could it be otherwise, right? And so once we dig into that, once we start from there, then we start to say, well, humans tend to organize themselves in various ways, or we think about institutions. Those change over time and space. It's not one kind of institution in which something like the disciplined study of the natural world has unfolded. There's been lots of kinds of institutions, and they changed over time and across space. The institutions themselves aren't just kind of, plopped down in a vacuum, right? Who wants that? Who's supporting that kind of research toward what ends? What do people want out of moving into those kinds of spaces? What do they hope to be able to learn or contribute, or why do they think they're doing it? And once we start asking those questions about the people, about groups of people, about larger groups that might be sort of supporting directly or indirectly those groups of people, then suddenly we have, a real history with a capital H. It's really in the flow of human events, and it's not kind of cordoned off as being somehow separated from the other elements that my colleagues in history are immersed in all the time.
Let's talk a little bit about your course, Einstein, Oppenheimer, Feynman, Physics in the 20th Century. So this is really bringing together the physics and history of science into this fascinating course. Could you share some of the main goals of the course that you have for learners?
Yeah, I guess I really have at least two big sort of high-level goals that I like to bring forward when I teach the class. And one is it really should help students, especially students in physics, but not limited to that, get a sense of a couple of the contours of the field. It can be a kind of, I sometimes joke, it's like a smorgasbord or a taster's menu, a buffet of what I still consider some of the most, mind-stretching, strange-sounding, delicious ideas at the core of modern physics. And that means things like quantum theory. It means things like relativity and gravitation and cosmology and astrophysics. There's plenty I have to leave out because of time, but we get to really sit with, early ideas about nuclear physics and where that leads to. So that part one is it's a kind of roadmap to some of the areas still of great excitement to the research frontier in physics today. They didn't come from nowhere. They've evolved sometimes, kind of a rocky, bumpy path, plenty of blind spots along the way. So part one is, what does the field look like now and how do we get there? Number two, coming back to what we talked about just a moment ago, how has this collective kind of community shared body of knowledge developed? And that brings us right back to its people in institutions set sometimes in very dramatic times, historical moments, wartime, fighting fascism, the nuclear age, lots of scary things, kind of worldly events. And that those, I say, weren't sort of separated from the march to better understand quantum theory or nuclear physics or the cosmos. So it's a way to try to see how do ideas and institutions kind of knit together and together change across time and space. It's not one versus the other. It's a kind of evolving framework of ideas and institutions, and that pairing, that kind of double vision, I find really helpful and a lot of fun then to try to engage, with the class as well.
Yeah. I mean, one thing that this makes me think of is like when students become aware of how institutions and physics kind of interact, they may begin to question their own institutions. Like, are women really represented in this field? And if they're not, then what impact is that having on what's being studied and what's being discovered?
Absolutely. No, that's a great point. And something, I've taught this course maybe 10 or 11 or 12 times over the years. I teach it roughly every other year. So I've had a chance to do it a number of times. And one thing I found adding more and more to the syllabus over time, there's room for more still, it's still an evolving course, are questions exactly of the sort that you're pointing to. And I'm lucky because some of my own historical work has focused on that, written in first round for kind of fellow specialists, but more and more of my colleagues in the field, in the history of science and in physics both, have been asking those questions and not just asking them, but really doing careful, empirical, archival research, interviews from more recent periods. There's more stuff that I can learn from and also more stuff I can assign and teach. So the reading list has been evolving. It'll continue evolving. Exactly on that baseline theme. This is done by people in times and places. That is non-trivial, we'd say. There's a lot going on there. Who's been invited in, who's felt welcomed in, and with what consequence, intellectually as well as sort of for the viewpoint more broadly of the scientific community.
Absolutely. And I'm wondering if that's one reason there's no textbook for the course.
Partly. It's still a somewhat unusual course. I have friends who teach similar courses elsewhere, so it's not this is the only one. And I've learned a lot from their versions of their courses. But I really haven't found the one kind of source that brings it together. And one of the things that's so special about this course here, that I enjoy in particular, I should say, about the course, is that it really is aiming first and foremost for physics majors. We can get into a bunch of equations, even though and we'll talk soon, I'm sure, the assignments are not typical problem sets. I love the kinds of assignments we get to do. But, in the course of a class discussion or during office hours, these are mostly, they're not entirely young physics students. So that's one kind of shared skills and shared reference points that we together can draw upon in the class. And to combine that with, readings about the rise of Nazism or kind of very context-heavy studies of women in science after the war, I haven't yet found one source that really knits them together in the way that I would want to kind of keep the material moving forward. So it's a kind of grab bag. Again, I revise the reading list pretty much every time I teach it, but there's a kind of pattern to it that I feel pretty comfortable with now. And that really is picking and choosing some papers, short papers by people like Albert Einstein that our students really can read and really make sense of, as well as works by historians, philosophers, sociologists, media theorists, or whomever else. And so bringing those together, and let's sit with those together is really fun. And that means let's just, put them together on a website instead of looking for one book that does it all.
Yeah. Yeah. And, I have to say the course is now on OpenCourseWare. It's an open educational resource. And now other people can remix those readings, change them around, supplement them, and it becomes a shareable resource, which is just great.
It's very exciting to me as well. And I'm sort of eager to see what other smart folks will do with it. I mean, here's my best take at it. What other people are going to do something else, which is great. Exactly.
So let's get into the details a little bit. Let's pick Einstein, Oppenheimer, or Feynman, some of your title characters. Like maybe pick one and tell me a little bit about how his context was shaping the science that he was doing.
Yeah, I mean, each of them, of course, are stand-ins for kind of generations. And so we talk about many more individuals than, of course, only those three. I did choose that title the very first time I ever taught the course with MIT students in mind. So what's going to catch their eye if you see a handwritten poster on the wall? But anyway. So, we spend a good chunk of the course thinking about Albert Einstein and the times of Albert Einstein, if not only his individual person. And I think, again, what's fascinating is that everyone more or less has heard the name. Everyone at MIT more or less has some ideas and maybe even some more detailed knowledge of some of the contributions to the scientific field that Einstein himself had created, or he in a small circle. And yet it's not always well known the kind of world he was immersed in, the ups and downs that he himself was facing individually, but again, even beyond the realm of just the individual. And so one thing I find helpful is, he was very, very ambitious and was mostly thwarted as a young person. And I find that actually kind of helpful to sit with for a little while, not to sort of point fingers and say, there was a kind of mismatch. And partly why he wasn't so successful is because he was extremely arrogant as a young man and also cut all his classes. It's a good thing to remind my students, don't cut your classes. Here's a pro tip. So Einstein got by basically borrowing the notes from a small circle of very good friends, one of whom then became his first wife, Mileva Maric, who was a much more diligent physics student and math student at the time than he was in university. Other friends who went on to very distinguished careers in mathematics and physics. And Einstein, as a young person, would basically delve into things he cared about and literally blow off or ignore things that he wasn't into, including if he wasn't impressed by a given faculty member. And that's not great advice. I always say Einstein was kind of a dummy. He was no Einstein as a young person.
Right.
And that's worth sitting with, again, at the kind of individual level. And then we can see, well, how was he beginning to ask questions that sometimes were on familiar terrain for the experts who were already the kind of esteemed giants in the field when he was sort of up and coming? He would ask what I think were often recognizable questions, but really kind of we might say, from left field, often with an unusual twist. And that's also fun to sit with. So the question we can say, I get it. I understand why that was a pressing challenge of the day. It fits into this body of work. Why is he doing things that looked then to his contemporaries pretty oddball? What do we do with it today?
Yeah.
And there's two kinds of oddballness that we can have fun with. One is we can read how did other people react to his work in real time. And we do a lot of the early reception, for example, of relativity. I think is just fascinating. And a lot of my friends in history have written brilliant things on that. But also, especially with a room full of physics students, most of whom have had at least some formal training, let's say, in special relativity before, it doesn't look the same as what we do today either. There's a strangeness that was commented on by contemporaries in the early 1900s. There's a different kind of strangeness as we as a community have learned and kind of assimilated this, and now we teach it in different ways than what made sense either to Einstein or indeed to his contemporaries. And so there's a kind of remoteness, which I find very helpful as an historian. It's not just what we all expect. It doesn't just look like what we did yesterday in our classes. Now, why not? That's an opening. Then to say, well, why? What made sense to them there? Why do we do things differently now? And how can we begin to tell a kind of more complicated, kind of ups and downs kind of story that stretches out, in this case, over many decades, roughly a century, and not just assume that because we still remember Einstein's name, we know what he thought he did. And that's really, we can sit with this looks familiar but strange. This is strange, but now I can see familiarity. You can do a lot of work with that kind of juxtaposition.
Yeah, that's interesting. And I know the course focuses a lot on science communication, writing in particular. And one of the assignments asks students to peer review a piece by Einstein.
Yes.
I mean, tell me about that. And how do students feel about doing that? That's a little bit intimidating, no?
It could be, but we work up to it. And so, again, my friends in humanities and myself would call this kind of assignment a very typical assignment. It's a close reading of a primary source.
Okay.
Take any history class or literature or art history or anthropology. That's a critical skill. To both read it and say, what do I think the author is trying to convey? What's the structure of the author's argument? What's the basis of the evidence to go from step one of the argument to step two? These are incredibly valuable analytic skills. And then to write, in this case, a brief paper, 4 or 5 double-spaced pages, not terribly long, where the students practice articulating, going through the argument. And it's, as I say, it's a close reading of a primary source because there's no library work. You don't have to read 3 more books and say what other people said Einstein was doing. Just sit with this text as a text. And in fact, only the first few pages of the text, just an excerpt. And say, here's what I think the author is doing to make an argument. And then the student says, and is it compelling? Is it a value? Is it a trustworthy argument? Are there gaps? Does it make sense or is it strange? And so part of what I remind them before they work on the paper is that many, many, many people who read Einstein's this very paper in real time back in 1905, they thought it was a very strange paper as well. It looked bizarre. It didn't follow their own standards or expectations from the day, much as it doesn't follow ours today either, despite differences between those two. It looked strange to the experts then. And very few people read this thing and said, oh, I get it now. I am reformed. The first response to Einstein's work in relativity was no response at all. And so we put ourselves back in the mindset, this is coming from basically little-known civil servant patent clerk, not a fancy university professor, who's writing things in an unusual convention and style, making some really curious-sounding arguments. Okay, let's sit with that. Here, read these first 5 pages of Einstein's paper, write 4 or 5 pages on your own, and that kind of, it's meant to restore some of the strangeness again. Pretend you don't know about what we all have learned, in the 100+ years since. Unusual paper, not already famous author. Let's read this on its merits. And I always say, the papers I enjoy reading most are the students who reject this. This is a bizarre-looking paper. This shouldn't be published like that. And I think they're often right. Yeah. So that's why we try to do a little more conceptual work by taking that excerpt pretty seriously.
And while we're talking about him being a patent officer, which I did not know, actually, what was the impact of his travels to and from the patent office that shaped how he was understanding the physical universe?
I love this part. And this I really take from a very dear friend and colleague of mine, Peter Gallison. I signed one of Peter's enormously influential and frankly just fun articles on this project. He went on to write a whole book about it, but for the course we read an article from Peter Gallison. And among the things that Peter does is he reconstructs, just as you say, literally the path that Einstein walked in Bern, Switzerland, when he was in his mid-20s, from his apartment, rather modest apartment, to his desk at his day job at the one of the many branches of the Swiss patent office in Bern, Switzerland. And what was so interesting that Peter was able to find is that Einstein was passing not just 1 or 2 clocks, he was passing a brand new set of special clocks that had just been installed around the time Einstein was making this daily commute, this walking journey. These were clocks that were coordinated, so they would show not just similar time, but really kind of lockstep time, long before the age of satellites and GPS and fancy things that we do to synchronize clocks today. But they were really a brand new invention just coming online around the year 1900, plus or minus, in many parts, certainly of Europe. And so what was most sort of surprising about Einstein's first paper on what comes to be called the special theory of relativity, this paper he wrote while at the patent office in 1905, was he's thinking all the time about how could one coordinate clocks at a distance. It's not so straightforward. And the solution that Einstein famously, very abstractly describes in this very abstract paper is we can use light beams, things like electromagnetic waves, radio waves. Now we might use lasers because we're fancy, but the same basic idea. Waves that are going to travel at a known speed. Einstein gets more and more concerned about the speed of light in general, and would it be the same for all observers? This becomes a core that he writes down in these strange-looking first few pages of this article that the students read so carefully. But one of the things he convinces himself of is that the speed of light should be a constant, independent of one's state of motion. I could be standing still on the sidewalk. I could be on a fast-moving train. We know Einstein loved trains. He often loved moving fast on trains. And that me on the sidewalk, my friend on the train, should measure the speed of light to be the same speed, even though we're moving at very different speeds from each other. So suddenly you have something like a standard bearer. There's something universal, at least Einstein had convinced himself, that's not only immeasurable, but it's not going to change kind of situation by situation. That sounds like a pretty good way to start standardizing clocks. One clock, sort of central clock, which you set by whatever means you want. You can say, that's my official time. And then you beam out time-stamped radio waves, because those are going to travel at a known speed. And if you know the distance you are from that central clock, then you know how long the light beam has traveling to get to you. So you know how much to offset your clock. And in fact, that part wasn't Einstein's idea. He was generalizing from it, I think, in really rather amazing ways. Again, I'm just learning this now, I say, from Peter Gallison's historical work. And so one of the earliest uses of the Eiffel Tower was actually to be a beacon to send out kind of standardized radio waves of standard central Paris time.
Really?
That people worried about this in an age of more and more trains moving more and more rapidly across more and more of continental Europe. You don't want to have different clock settings at the start and end of a train journey, because that could lead to, terrible things, crashes and let alone hard to schedule. So the real world demands, civilian and military, it's a time of still great unrest, the Franco-Prussian War of 1871 and 2. I mean, all these things are real world concerns during Einstein's own kind of youth and as he's growing up in that world. So there are lots of clever engineers and scientists thinking about trying to make sure clocks were comparable. Some people who said, let's use radio waves. Einstein was growing up where that was more and more becoming a fact of life. Literally, as he walked to his office, some of the clocks he passed in the streets of Bern were some of these newly coordinated or synchronized clocks.
Yeah. What I find so interesting is that your take on this and your colleagues' take, it's not just like institutes and culture and politics that shape how science is done. It's like the physical spaces themselves.
Yes.
And that's what I find particularly new about this.
I agree. And then we can trace it back the other direction, right? Once some technologies like those become common or standard, how does that act back on the worlds of institutions, politics, culture? And so they're not separated, and they're also not only flowing sort of from one to the other. It really is, a fascinating model as opposed to a frustrating model. I think seeing these kind of eddies moving in multiple directions, I find that just fascinating.
Yeah. So I have to ask you about the Oppenheimer movie.
Yes.
For a second. So I saw it in preparation for this interview.
Mm-hmm.
I brought my snacks, stayed the full 3 hours.
Good.
It was great. So what did you think of the movie? And what did they get right? And what did they get not right?
I was really impressed by it. I've only seen it once. I saw it in the theater.
Yeah, first of all, this is your jam.
It's my jam. And it's kind of it's like pinching myself.
It's like they made it for you.
Well, for a small set of my friends, at least, it's very delightful and exciting and a little bit strange.
Yeah.
I'll share a quick story. I worked with a wonderful, wonderful younger scholar. I was on his dissertation committee, Sean Mullett, historian of science. And I saw Sean just recently after the film had been released. I hadn't seen him in quite some time. And he described he had an out-of-body experience in the theater because he hadn't realized that the person he focused most of his thesis on, an otherwise not well-known figure who'd been a PhD student of Oppenheimer's at Berkeley in the 30s, that an actor playing him walks into this major production and says these things that Sean said, yeah, that's basically what he would have said. So Sean didn't even know to expect the kind of lesser known characters that on whom, a few of us have focused so much. So that was kind of my feeling as well. So I was impressed by the film very much cinematically. I know the book on which it was based quite well, and I've taught that book in other classes. I knew the authors pretty well. And so when I heard that would be the basis for the movie, I was a bit more confident. And I thought the attention to historical detail overall for the film was amazing and much more than I would have expected. Of course, there's license because you have to fit merely 700 pages to 3 hours on the screen. Lots have to be creatively done there. But I thought the filmmaker, Christopher Nolan, and the whole team were really, to my mind, very impressive at their goal of a kind of conveying still relevant, big feelings, thoughts, ideas, and emotions, while also being anchored to very specific historical documents. I knew when this actor says this line, I know exactly what it's being quoted from, is line by line from this or that, hearing that was held in 1954. And that level of kind of attention to historical detail I found really terrific. And to put it together in a way that these artistic folks can do was very moving to me.
That's great. I'm curious about the Trinity test in the movie and particularly about the communities that were downwind of that test. And I'm wondering if in general, those narratives tend to be left out of the historical narrative, or what your take is on that.
It's a great point. So there are thankfully many, many historians and anthropologists and sociologists and public health officials and scientists themselves who have in more recent years gone back and filled in some of that essential historical work. So we as a specialist community know much more about that than even we did, let's say 20 years ago, let alone 70 or 80 years ago. So there's more to draw on when I teach this material. There's more that I can read and share with students as well. More to be done, but more than there used to be as well. What I find fascinating is related to that. It's not only, it includes, but not limited only to folks who happen to be in close proximity to that one explosion, but also to the hundreds of thousands of workers, certainly tens of thousands at very specific large plants during the Second World War, who were given very little information about the very, very harmful materials they were handling. So one thing that we talk about a lot in the class that the film could maybe have done more to illustrate, but certainly we spend a lot of time with this in the class that's now on OCW, is that the Manhattan Project, depending on one counts, formally employed anywhere from 125,000 to 500,000 people during the war, depending on what categories you kind of lump together. Huge. It's not Oppenheimer and 12 geniuses on a mountaintop by any measure. I mean, hundreds of thousands of people, the vast majority of whom were given very little information about what they were actually handling or why. It was, of course, a highly secret classified project during the war, and so much so that there was internal kinds of classification. And so in addition to the so-called downwinders, people who are actually employees of the project at huge industrial plants like in Oak Ridge, Tennessee, like in Hanford, Washington, these were put together in a real hurry to produce larger amounts of fissionable materials to scale from kind of micrograms to kilograms. That's a large shift in a wartime setting, very time sensitive. And they had to do that by using really poisonous conventional materials, let alone the special nuclear materials. Some of the epoxies, some of the dissolvents, they're horrible, horrible materials. And we now know, again, through historical work over the more recent decades, how little those workers were informed, even though they were on the project, let alone the people who happen to live, say, in New Mexico near the test site. And so I'm not trying to belittle. I think that being near the first explosion would not have been good. And as we now know in hindsight, that was the first of many, many above-ground explosions that were done after the end of the war to test next generation's bombs. So you have an accumulation. One blast might or might not have an immediate effect. Many, many, many over now decades. That's not a good thing to be near, of course. And even during the war, prolonged exposure, even for 2 or 3 years, to these highly, highly toxic substances, not at all good. And there are indeed now documented intergenerational elevated bad health outcomes at other sites like that. So we now know a lot about that. Now, sometimes people will say, oh, but nuclear weapons were literally brand new in this time period. Did people just not know what the risks would be? And I think that's giving some folks, too quick a pass. The public health community knows a lot more now than then, of course. There was a lot known even then about some of the dangers, the health dangers of certain kinds of radiation. So I don't think the fact that people know more now means that it was a reason not to have been much more carefully informing workers and neighbors, let's say, people living near at the time. So, it's in one ways a teachable moment. This is wartime. The Cold War came next. That's not to excuse it. Can we try to understand how that ever could have seemed like a reasonable policy for the United States government to have adopted in secret? Not to endorse it, but say, how could that have been? And then with that knowledge, what might we try to do now moving forward?
Yeah, no, thank you. I wasn't aware of that aspect of this, so thank you. Mm-hmm. I want to move you now, before we talk in more detail about the course, but just to the Cold War. OCW works with community college faculty who are adopting and adapting OCW content. And I had the pleasure of speaking with a history professor as part of the Maricopa Community Colleges. Yeah. And he had a question for you.
Great.
Because he knew I'd be interviewing you. Mm-hmm. he's interested in history and the impact of technology and all of those things. So he says, his name is Paul Heider, and he says, how did the technology that ignited the Cold War influence changes in American culture?
What a great question. Thank you. And thank you, Paul. First of all, what technologies might we have in mind? That would certainly include things like nuclear weapons. That would include also lots of very fancy electronics, some of which was actually pursued here at MIT during the war for the radar project, at least as impactful on the course of the war itself, and also with hindsight, we know, unbelievably important for the consumer electronics revolution that was soon to come and much beyond. So we can think about the kind of modern electronics, the shift from vacuum tubes to transistors, which happens very soon after the end of the war, all kinds of extremely precise kind of microwave technologies that are hidden from us, and yet we still use all the time to this day. That leads to communications. Soon it leads to rockets and satellites, part of which also had a wartime, of course, origin. And so when we start knitting these things together, not so long after the end of the Second World War, rockets, incredibly powerful clocks, soon lasers, what hasn't been impacted by these things? And some of it is for further kind of wartime-like weaponry of increasingly, kind of lethal and fancy kinds, of course, and we might associate that with the Cold War first and foremost. But it also leads to things that many of us simply might take for granted today. A project I've been having a lot of fun working on as an historian is on some of the early history of the Global Positioning System, or GPS. So that's not coming out, in 1946. It's operational already by the mid to late 1980s. But you can draw this really, very careful kind of direct set of connections to a lot of this wartime surplus stuff coming out of the Second World War. And that gets us to things like atomic clocks, atomic frequency standards, clocks that will be accurate to nanoseconds on a day and not much, much more jitter than that. To things like lasers or other very accurate electromagnetic signaling devices, to very rapid computer chips. You put those together on satellites moving, high above our heads, and suddenly many, many people in the world, around the world, have devices in our pockets where we can learn to a roughly 1 meter accuracy where we are. And that comes from an unbelievable assemblage of basically quintessential Cold War technologies, most of which were actually put together for military purposes first. GPS itself was originally a classified military technology, drawing on basic ideas about physics and engineering, but getting an awful lot from kind of more direct Cold War spin-off kinds of developments. And so once we get to something like GPS, how I find my way, when I'm lost in my own kitchen because I have a terrible sense of direction, then what wasn't touched is really, I turn the question around. I like Paul's question a lot, but it'd be harder to answer what hasn't been affected, even in very kind of ubiquitous, mundane daily life, by a whole set of technologies and also kind of things we've learned about how the world fits together, that we can draw pretty straight lines back to this enormous kind of confusing, often very scary and deadly time of the Second World War and the early Cold War.
Yeah, so interesting. I have so many more questions about that, but I will move us on. I just wanted to touch on another film, which is Containment.
Yeah.
You watched that in the course. Mm-hmm. Could you tell us what that film is about and what kind of discussion it generated in the course? It's
a fascinating film. It's a documentary, roughly 90 minutes, which I would say is perfect because the class time is 90 minutes. So I'm not asking students, to do more than they would invest in a lecture session anyway. The film was made by Peter Gallus, the same colleague I mentioned earlier with Einstein's clocks. Peter is a remarkable filmmaker as well as an historian and a physicist. He and a team made this film, as you say, came out only a few years ago. And it's a nonfiction documentary about efforts to contain basically nuclear waste from now generations of the nuclear age, not just from weapons development, but also from civilian nuclear power. And there's just many, many kinds of very, very long-lived waste products, some of which are still very dangerous to people and the environment and to, animals of every kind, and that don't lose their toxicity very quickly. So some of those kind of half-lives of some isotopes of plutonium are measured in tens of thousands of years. So if you have a so-called if you have a radioactive sample here now, it's not going to be safe for longer than, there's been written language. I mean, getting our heads around that kind of timescale. So this fascinates Peter, it fascinates me, but Peter made this film some years ago. And they're really just trying to trace through up to quite contemporary times, as the film was really being made, what are different ways to grapple with a different kind of legacy of the nuclear age? It's one thing to think about kind of mutually assured destruction and brinksmanship and how this drove domestic and international politics. And we talk about some of those things even in this class. Those remain incredibly important. We still have to worry about nuclear weapons to this day with active war in parts of the world. So these are not merely bounded historical questions there. And what I've really had my eyes open to from work like Peter's and other scholars is there are other dimensions that also haven't gone away that also stem from, the onset of the nuclear age. And that needn't lead one to one side, civilian nuclear power, love it or hate it. It's not going to be decided as a kind of vote or a coin toss. But what I think the film does for me in a very effective way is make visible for us what in my head was otherwise, it was very abstract. The amounts of waste of really dangerous stuff has to go somewhere. And the community has yet to find a really foolproof kind of way of dealing with that. And it has effects on communities, mostly poor, mostly communities of color. Like the story of the downwinders, we have versions of that going on to this day, not only from above ground nuclear testing, but from related, activities. And again, it could have been pursued with intentions we might understand during the Cold War or trying to provide civilian power. It's not that it's about heroes and villains. It's about, trying to understand a wider range of impacts and some very dear costs from, again, kind of quintessential Cold War technologies that haven't gone away. They're not merely historical. They haven't literally been contained. And so the film called Containment is how, among other things, how do we contain this ongoing legacy? Because sort of we haven't found a great way to do it yet.
So just to sort of wrap us up here, I'm really curious what you've learned about yourself as an educator over the 10 or so times you've taught this course?
I love teaching this class. I mean, I still love it. I'm going to teach it this spring. I'm so delighted I can do it in person again, and really see and interact with students, not only via screen. So I'm excited to do it again. I mean, it's a class that I get excited about every time I get the chance to teach it. One thing I've learned about myself is, which I really value, is that it's okay not to know stuff. And so when I was a young professor, and I don't think I was alone in this, I felt like, I better just know. What are any questions that comes up? I better, it's my job to know. And it took a few iterations to say it's my job to help us all figure it out, which is very different from like being a wizard who just knows everything. No one's like that. No reason to think that's the right goal. And so to be even a few more steps in a kind of collaborative, let's learn about this together, which has been good for me and hopefully helpful setting a kind of a better group learning philosophy, let's say, for the class as a whole. I used to do a thing, now I give a kind of a last lecture for the class. I try to wrap up threads and, it's included on the OCW set. Before I developed that one of the lectures, the 25th lecture for the class, I used to do a game for the last class sessions. I used to call it Stump the Chump, but I stole that from the Car Talk guys, I think. I just love the phrase.
Yeah.
And it's like the floor is open. We've covered some amazing ground this term from, early 19th century physics. The course actually starts well before the 20th century. And by now, pretty several steps into the 21st century. We've got a lot of stuff on the table that we got to really sit with together over the semester. Myself, the students, the teaching assistants. What's left? What do you want to know about? And just let the students just ask questions at random. And to make myself, again, kind of vulnerable in an exciting way to that.
Yeah.
Because first of all, these are, as I said before, these are just unbelievably talented young people. And they don't have all the answers either, but they're so curious and engaged, and they're engaged right up through the end of the semester, which I'm just grateful for. They're still showing up, and they're still reading, and I read this and I'm curious about that, and I heard this thing in the other class. I mean, that's one of the great gifts of making a life in a university. And so it was that experience when I realized I should ask them any question they want to ask and let them know that, wow, that's a great question. I appreciate the question. I have no idea. Let's go work on this together. And that's something I've learned about myself, that frankly, it's more fun for me, hopefully a bit more interactive for the students as well.
That's great. That's great. Thank you. What advice do you have for other educators who may want to engage their students in thinking about the history of science?
Well, there's a lot. And I think there's more and more hopefully helpful and interesting resources out there. I'm so delighted that this course is now available, and it's all through Creative Commons licensing, and the slides are there and readings. I mean, people should make of it what makes most sense for them and for their immediate pedagogical goals. And it's not only this. I mean, there are lots and lots of, I think, really high quality materials out there, published articles and books, many of them very accessible now, not only kind of written for a small circle of specialists, lots of creative multimedia things. I mean, courses like this and a few Google clicks away can get to other, I think, exciting materials from very talented colleagues. And then the instructors can kind of make it modular, can pick and choose. It might be that they want to include one special class session and not revamp their entire class. I'm sure they have other learning objectives and things they really want to cover in their existing classes. But there could be maybe inspiration to tweak, to add one more reading, maybe one extra class discussion, and maybe that leads to the next time. So I think what's nice is to think about it kind of scale. And if the overriding theme is that this is done by people in times and places, we're all fallible, we can try our best, we do better when we have a larger community and you have more eyes and hands that work together, we can try to convey that, I think, really important lesson through history and the history of science. And you can get that across, with one extra reading or one class session, as well as maybe a whole semester or beyond.
Yeah, that's really helpful to think about it in terms of scaling up. What else would you like to add that we haven't addressed about teaching physics, history of science?
Well, another thing that I really love about this class is that it's mostly physics majors, not required. There's no prerequisites, but it fulfills what at MIT speak is CIM, which means communications intensive in the major. So it helps physics students fulfill a major requirement. Others can take it as an elective, and they do very well. But what that means is what we practice in the class is mostly writing. It's a big class. I haven't figured out how to do kind of oral communication, which is also critical. Yeah. Students will get that in some of the other classes, of course. But at least kind of clear, concise writing, building on a range of sources, making an argument, having a structure, that those are skills that are at least as important as remembering where the factors of 2 pi go in these very important problem sets. And so I always joke that my friends and colleagues in our department here, they'll teach our physics majors how to calculate really well. Our students calculate great. There's no question. Let's make sure we're not losing other really important skills as well, or giving them kind of short shrift, so to speak. And so that's one thing I loved working on in this class, is we get to sit with these amazing ideas and read original physics papers, as well as work by historians and philosophers and, in media studies and well beyond, and try to put a kind of conceptual story together about ideas that I still just dearly love in physics itself. But we're going to practice sort of talking about those, making arguments about those, adducing evidence about change over time, in a way that their students don't always have that same opportunity in all their other otherwise really quite wonderful classes. And I love the opportunity to work on those particular kinds of skills with students who are immersed in this fun set of material.
Do they ever come with anxiety about writing, and how do you tackle that?
Many of them do. And I find that curious because the students who are coming to MIT, by and large, had done extremely well in high school, including in kind of classes that had heavy writing compared to. So it's not like they never wrote a 5-page essay before, or even by the end of the class, a 12-page essay. So one thing, but nonetheless, the anxiety, I think, for some is legitimate. I think they either haven't exercised those kind of muscles in a while, or they feel intimidated now that they're at university and not in high school, whatever it may be. So one thing I find helps is actually break down the process into smaller parts. And so each of the essays sort of builds on the previous one. So I don't ask the students to write a 12-page research paper on day 3. That would be silly. But we say, let's write 4 pages, double-spaced. That's just a handful of paragraphs. Like I say, no need to go to the library, like a close reading of one source. Let's work on transition sentences. Let's work on topic sentences. Let's work on, evidence and footnoting. Just little pieces that are not going to blow their minds. They are absolutely up to the task. Let's sculpt it so it's really kind of pretty, user-friendly. Go over it with them. They can rewrite it if they want, right? Then for paper 2, okay, let's do that. Let's make it maybe 6 or 7 pages. You just did a little bit more. Let's build on 3 to 5 readings, not just one, but just kind of baby steps out so that each component of this can be kind of sat with and practiced instead of just sort of dropping it all at once. Say, okay, just come back and tell me when you've written your paper. And likewise for the last one. Another feature that I really admire about MIT's communications intensive courses generally is that at least one paper must be formally rewritten as one of the assignments. And then in my class, and I think many of my colleagues, we make it an option. Students can rewrite any of the papers. And why is that important? I've been writing stuff for a long time. I write essays, I write books. I have to rewrite my own stuff all the time. Revision is itself a kind of skill that maybe, again, doesn't get quite the kind of emphasis in some other classes. So it's not just that we can break down topic, sentence, transition sentence, footnotes, argument structure, but also you're going to come back to this with fresh, you'll get feedback from myself, from teaching assistants, maybe from some of their own peers. And revising is itself a cool skill. And no one's born knowing how to do that either. We can work on that. So I like that kind of expansiveness, taking the whole semester to go from modest, contained, well-defined little bit, and then say, you can do it, and now let's add in a few more kind of moving parts. And I find that, and the students do very well with that. I mean, they're very successful, I think, because we can just kind of demystify some of the steps along the way.
Yeah, absolutely. And it also shows that it's not an innate skill. You're not a good writer or a bad writer. It's a skill that you develop. I have a lot of people on this podcast who talk about math that way. Mm-hmm. A lot of MIT professors who do math for a living. And they say, I wasn't, a natural mathematician in high school, but someone told me, in fact, our previous guest, someone had to tell her, you're having a hard time not because you're bad at this, but because it's hard.
Right.
And then she treated it like a language and learned and practiced. And what you're saying is the same with writing, that it's a skill that can be practiced.
It is. And I look back on my own, training from some of the folks I mentioned earlier. I mean, Naomi Oreskes, when I was an 18-year-old, first-year college undergraduate, she was so unbelievably generous with her time. And Rich Kremer was as well, the other historian. The number of drafts they must have, sat and or suffered through of mine, either way. And it was just cogent and constructive, and we can work on things at this scale, and then we'll build towards those. What did I know? And it's not like I learned it when I was 18 and had it down by the time I was 19. Of course not. And in my own career as an historian, I've been very lucky to work with really, really good editors.
Yeah. Yeah.
And I've been learning this, still learning and still practicing now. I've been doing it for a long time. So I still enjoy the kind of, it's still, something that I get to practice and learn about from, experts for whom this is their day job. And so to bring some of that, again, kind of demystification, no one's born doing this, and it's learnable. Mm-hmm. And these smart kids are good at learning stuff, right? So we can help them along with that, much as they're being helped along and flourishing on, the full gamut that they're having in their other classes as well.
Yeah. Well, David, thank you so much. This was really delightful.
Well, thank you. I'm really so glad to be able to talk with you, and I'm really delighted the class is now up there and available more broadly.
Oh, we are too. Thank you.
Thank you.
That was our conversation with David Kaiser, MIT professor of the history of science and physics. He's the instructor for the MIT course called STS-042J, Einstein, Oppenheimer, Feynman, Physics in the 20th Century. His teaching materials from that course are available on our MIT OpenCourseWare website. You can download, use, and remix his open educational resources in your own teaching and learning. Thank you so much for listening. Until next time, signing off from Cambridge, Massachusetts, I'm your host, Sarah Hansen from MIT OpenCourseWare. MIT Chalk Radio's producers include myself, Brett Paci, and Dave Lishansky. Show notes for this episode were written by Peter Chipman. David Kaiser's OCW course site was built by Kathleen Nalizetti. Jason Player made our episode cassette animation on YouTube. We're funded by MIT Open Learning and supporters like you.